Welcome back, my friends, to STEM Marin, Physics and Engineering, week 5? Are we in week 5 now? I have no idea. Yeesh. Time flies or drags slowly when we are doing asynchronous learning. Okay, so the plan for today is we are going to have our second foray into your textbook. Today, we are going to be cruising through chapters 4 and 5. So you will need your science notebook out. Pull out your science notebook. Go ahead and open it up to page whatever this is the next page that you're on. 10, 13, whatever page it is. Make that the page. So I'm going to go through and we're going to take some notes as we go. I'm going to write down some stuff, but not everything. So some of the stuff I will intentionally tell you I'm not writing this down because it's somewhere else. The two places where you'll mostly find things are, number one, your physics everything sheet. All of the equations are on your physics everything sheet. And number two, the page number 2 in your notebook, which was the Newton's laws notes. Okay, so some of the stuff will be on page 2. Some of the stuff will be in your physics everything sheet, and some of the stuff will be in the notes that we're going to take right now. So with that, let's get going. Okay, so you're opening up to page 43 of your textbook. Page 43 is chapter 4. And let's start at the very beginning. We're going to go through chapters 4 and 5. And so let's title it, there it is. Let's title it Chapter 4, Inertia, and Chapter 5, Force and Acceleration. And again, you make the page number whatever the page number should be. So maybe it's page number 10, maybe it's page number 13, maybe it's somewhere in between those numbers or past one of those numbers. Who knows? Okay, so let's start at the very beginning. Aristotle on motion. Aristotle was a Greek guy a long time ago, and he had this idea that stuff doesn't just happen from nothing. Something causes things to happen. Specifically, he said, why would something move if nothing pushed it, if there was no, what he'll call a force? So came up with this idea that things only move when there is a force. So if there is no force on an object, it will continue to do whatever it's doing. That may sound familiar because it is really similar to Newton's first law, which we'll get to in just a second. If you flip onto page 45, like this one, there are some nice little diagrams showing a ball going down a ramp. Here we go. So ball going down the ramp means the speed increases. Gravity is pushing on it and accelerating it downwards. The ball going up the ramp, it's slowing down. You probably have some life experience here. And then ball with no ramp, the speed just maintains the exact same speed. So things speed up going down, slow down going up, and then maintain the same speed if there's no slope. You can then apply that into a few little skate ramp things here. So if I go down and then back up, it'll get back to the same height, assuming no friction. If I change the shape, it'll still get back to the same height. If I go down and then there's no back up, it'll just keep going indefinitely, keep going forever. Okay, so all of this is kind of an explanation of Newton's first law, the law of inertia. I am on page 46 now. So Newton's first law, the law of inertia, is written on page 2 of your notebook. And it said that an object in motion remains in motion. An object at rest remains at rest if there are no other forces acting upon it. So assuming there's no friction, assuming there's nothing stopping it, it'll just keep doing whatever it's doing. Okay. However, sometimes there are forces that act upon it, and this is on page 47. And one of those forces that could act in opposition to something is friction. So friction is when you have a force in the opposite direction and it causes things to slow down. So friction is a force that acts opposite motion. We could also say that friction is a force that opposes motion. So if I had a little diagram here, if I have a ball and that ball is moving forwards like that, right? That's my velocity. Then the direction of friction would be opposite the velocity, right? So my friction force would be going backwards. Because if it's pushing this way, the ground will be rubbing against it, pushing back the other way. Okay, let's flip on to page 48. Page 48. 48, there you go. And we're going to look at mass. So mass can be a measure of inertia. It's a measure of how much the object will keep doing what it's doing. A quick note that mass is not weight. So mass is not weight. Mass is the amount of stuff. It's the amount of matter in an object. We have that definition on our physics everything sheet. So it's the amount of matter in an object. Weight is the force of gravity. So because it's a force of gravity, I could also say that weight is equal to the force of gravity, and a force is equal to the mass times the acceleration due to gravity. So the weight is the mass times the acceleration due to gravity, or since I know that the acceleration due to gravity is 9.8 meters per second squared times the object's mass. And that weight will be given in the unit newtons. I could also give weight in pounds. That's a different form of weight, a different force unit. But for most of the time, we're going to use newtons as our force. So I would measure my weight in newtons because it's, and I'm assuming we're on the Earth. Your weight can change if you go to different planets. So if you're in different gravitational fields, if you go to the moon, say, which is technically not a planet, I know that I just said on different planets, but the moon is a moon, then your weight would be 1/6 as much because the moon is much smaller than the Earth is, so it has less acceleration due to gravity. The acceleration due to gravity right here on the moon is about 1/6 as much. Your mass would stay the same. You have the same amount of stuff inside of you. So your weight would become 1/6 as great. Assuming that we stay on the Earth, which for most of us is a safe assumption. I so far have lived my entire life on the Earth, and I plan on living the rest of my life also entirely on the Earth. Assuming that we're on the Earth, then we always have that acceleration of 9.8 meters per second squared. And then I can do a pretty easy conversion from kilograms to newtons. So I could say that 1 kilogram is equivalent to 9.8 newtons, since it'll always have 9.8 meters per second squared of acceleration on it. I also could convert it to pounds. 1 kilogram is about equivalent to 2.2 pounds, as long as I'm on the Earth. And then if I wanted to go newtons to pounds, there are approximately 4.45 newtons in 1 pound. So if you just say, like, rough estimate is 4.5, right? If I take my mass, my weight in pounds, my weight in pounds is around 150. 150 times 4.5, 150 times 4 is 600, 150 times 5 is 750. So I'd be around 675 newtons. Okay? So a human is about that size. All right, let's flip on to page 50. On page 50, it talks about net force. So net force is the total force. Okay? So over here, net force, I can abbreviate it, F net, right? I'm using a subscript. And that just means the total overall force. right? So after I take everything minus everything going the opposite direction, what am I left with? Okay. So there's a nice little diagram here. If I'll show you, here you go. Not that, not that, camera, camera, there we go. Okay, so here's a nice little diagram. It shows that the applied forces in the first example right here, I have 5 and 10 going in the same direction. So that adds up to a total of 15 newtons over here. My next example, I have them going opposite. So I have 5 newtons going in one direction, 10 newtons going in the opposite direction. 10 minus 5 gives me a total of 5 newtons going in the right-hand direction. We normally set right as positive, so there are 5 newtons in the positive right direction. And then finally, my last example would be 5 newtons in one direction, 5 newtons in the other direction. 5 minus 5 gives me a net force of 0 newtons, which means it just stays still. No acceleration. All right. So equilibrium. Equilibrium is when I have my forces balancing out. So it'd be kind of like that last example. The force down equals the force up. So when I say right here, I am in equilibrium. Okay, so equilibrium is when the force down equals the force up. Or the force to the right equals the force to the left, or the force up and to the right equals the force down and to the left. I could be in all kinds of different directions, but for now, let's go up and down. So when that's the case, I can create some ideas and figure out kind of like what's happening. So one thing I could do is I could say, let's say I have an object that has a force of 10 newtons. Okay? That object is hanging from a rope. And then how much force is the rope pulling up on the object? Well, if the object is going down at 10 newtons, that's its weight, then in order to keep it in equilibrium, in order to keep it in the same place, it has to get pulled up by 10 newtons. So the force up of the rope would equal the force of the weight down, right? So this would be the weight, and this one I'm going to call tension, T. That's the force up of the rope. What if instead of having one rope holding me up, I had 2 ropes holding me up? In this case, I still have the same weight going down at 10 newtons, but now I have 2 ropes going up, 1, 2. Well, 10 gets split into 2 ropes now, so each rope would hold 5 newtons. 5 plus 5 gives me 10. Nice. And that's shown on page 53. There's a little diagram showing my different spring scales holding my weights. All right. Now, the other component is we can add vectors. So vectors are arrows that have angles, length, and magnitudes. And it turns out that the the more gentle something gets, the harder it is to hold, the more tension you're going to get. So I'm going to do a little example. I'm going to kind of show how I might hold myself up using some angles, and we'll see just kind of like how strong or not strong I am as we change the tension. Okay, so I am going to flip this around this way. There we go. Go like that. Tilt so that you can see there. Lovely. Okay, and can we see that gap there? Yes, we can. Great. So if I have 2 tables here, and I have them sitting side by side, and I've been working out quite a bit, no big deal. So I have a mass of 65 kilograms, a weight of what I said was 675 newtons. So If I have it on 2 hands, then each hand takes half of that. Each of my arms takes half of my 675, so each one's taking like 340 newtons. Right? So I go like this, I lift my hands up, and I can totally do that. Right? Each arm holds 340 newtons, no problem. Right? And it's going straight up and down. But what if I move them out? So if I move it out a little bit, now they're at an angle. So now I still have the 340 going down, but I also have this sideways component. And that sideways component means that the total tension on here is going to be greater, right? I'm going to have more 340 plus the Pythagorean theorem, a squared, b squared, c squared. The arm has to hold c squared. So if there's 340 going down and then 200 going this way, my arm ends up with 400 newtons of force. That was just an estimate. So I'm going to hold it like this, and oh, I can still do it. Nice. But it's hard. I'm shaking a little bit. Okay. Now, if I go even further, that more, now my angles are like this. Oof. That's going to get tougher. Let's see if I can do it. Oh, it's really hard. So I get out to here, and I try to lift my hands, and I can't do it. I just fall straight down. I am not strong enough to hold up, 500 or 1,000 newtons of force. My arms just aren't strong enough, so I can't do it at that angle, right, on the shoulders. So if you have ever watched gymnastics and you have seen them do on those rings, the 2 individual rings, and they're hanging from the rings like this. If you're hanging from the rings like this, no problem, right? I can hang on a bar. I'm taking my weight and splitting it onto 2 arms. But if I try to pull myself up like this and hold myself like that, well, that's called an iron cross. And it's taking all of your weight, still going down, but now you have this enormous horizontal component. So in order to hold yourself at close to steady and close to horizontal, you have to be wildly, wildly strong in the shoulders. So that is super duper hard to do. And technically it can never be perfectly straight. You're always going to be slightly up or slightly down because you need some vertical component for your weight. Cool. All right. So let's flip back around. Whoop, hope you didn't get dizzy there. And keep it going. Oh, I'm out of breath now. That was hard. Got to do easier demonstrations. Okay. So there are my 2 diagrams. You can see that they still, you can't see because I have stopped sharing. Let's do that instead. Sorry. Now, once I figure out how to share it, now you can see again that I have 2 diagrams. One right here, right? And that's at a kind of gentle angle. Actually, I'm going to make this even steep, like even more gentle, really show that these are super gentle there. So I've got a box here, and then I've got one like this and one like that, right? Those are really gentle. And all told, they add up to my 10 total. Now on this one over here, I've still got my box, right? But now my angle has gotten super big, right? There's my angle. And because it's such a big angle, they still add up to 10, right? If I do, that part is 5. And then over that way, that part is 5, right? So that's 5 on that one and 5 on that one to make my total of 10. But it also has this huge horizontal piece. So these end up really long and lots of force. Good, so that was much harder. You can remember me on the table or not on the table, falling over, because I got to work out a little bit more. Eh. Okay, let's flip over again. Inertia in action. Okay, so the other piece is thinking about inertia in action. So we said that an object in motion stays in motion, and that's relative to the person who's holding it. So I'm going to try something. I don't know if I can actually manage it, but here we go. I'll do the same deal. I'll flip around just a little bit, and I'll try to do a little run. So if I am standing in one place and I have my keys in my hands, and I'm standing still, and I throw it up, they'll come right back down into my hands, right? So I go up, down, and I just kept my hand in the same place. Well, if I'm walking, then from your perspective, as I'm walking, the keys will go up and they'll do like a parabola. They'll go up and then they'll come back down over here and they'll still be right here. From my perspective, I'm going to throw them straight up and they're going to land right back in my hand. Let's see if I can actually do it. So I'm walking, they go up, and they came right back down almost in my hand. I'll try it again because that was a bad catch. Up, back down, my hand never moved, but you saw the parabola. I could even do it faster, he says with stupid confidence. So if I'm running, up, down, end of the table, bad idea, but they're still in my hand. From my perspective, the keys go straight up and straight down. The horizontal motion is consistent. So it's an object in motion, staying in motion horizontally as it goes up and down. Horizontal motion is independent of the vertical motion. Oh. All right, so I'm going to keep you on this kind of screen for a little bit because we're going to briefly zip through chapter 5 as well. And we're going to zip through it because we've already talked about it all in the Newton's Laws notes and on your Physics Everything sheet. So starting on chapter 5, I have acceleration is the velocity divided by the time. You know that. We're good. Force causes acceleration. We have an equation for that. It's that acceleration is inversely proportional to mass and directly proportional to force. I can rewrite that as acceleration is equal to force over mass, or F equals ma. That's Newton's second law. It's in your Physics Everything sheet as the equation for force. Lovely. Flipping on. Friction. So friction pushes against the motion. So I like figure 5.5. It shows two different types of side of the road stops. One is metal on the side and the other is concrete down at the bottom. So which design is best for slowing an out of control side swiping car? If I want to slow the car down, the one that I want is this one with the concrete because it's going to rub up against the tire. Rubber on concrete is going to be a lot of friction and that'll slow it down. If I just want to redirect a car, like on the side of a cliff, if I'm driving along the beach and I want to make sure that the cars don't go over the cliff, this one is great because it's really smooth. It'll just kind of redirect and push them around the other way. So you can use friction to kind of benefit you. Pressure. And we also said that friction opposes motion. So the push goes one way, the friction goes the other. The weight goes one way, the air resistance, which is a friction, goes the other. Pressure. Pressure is equal to force over area, P equals F over A. And I believe that we have that in our Physics Everything, although we may not have added it. We might have to add pressure to our Physics Everything. Pressure is force over area. Free fall says that every object falls at the same rate. So if I drop two objects and no air resistance, they all have the same acceleration down due to gravity. We can double check that. In fact, let's double check that. Let's take two objects of wildly different sizes and drop them. So Here we go. You'll need to see the ground again. Object number 1, a textbook. Object number 2, I'll choose something bright. A bright green, yellow shows up better. A bright yellow highlighter. They obviously have very different masses. The highlighter is much lighter. The textbook is much heavier. If I hold them up high and drop them together, 3, 2, 1, go. They fall at exactly the same rate and hit the ground exactly together. So if you can watch it in slow motion if you like. 3, 2, 1, go. And they fall right together and hit the ground together. And I'm sorry about that loud noise. All right. Back around. This is kind of a hot one. Let's see, we're back on chapter 5. That's the downside of closing all of my pieces. Oh, for pressure, just another cool one. That like bed of nails thing is that you can stand on a bed of nails because you're putting the pressure or the amount of force over lots and lots and lots of dots. So it doesn't feel bad if you have, let's say the options are either somebody stomps on your hand with just the point of a high heel. They're taking all of their weight and putting it down onto that tiny little dot at the end of the high heel. That would really hurt. Or somebody lies on your hand or sits on your hand with their butt or their belly. Well, that wouldn't hurt very much at all because it's a lot of area. I'm spreading all the force over the entire area, not going to do any damage. So that's where pressure comes in. I'm taking the force and dividing it by the area to figure out the pressure. Okay, so the pressure would be like why sharp things work. Same force, but put onto a very small area, lots of pressure, splits it apart, like a knife or a pin. Okay, terminal speed. Terminal speed or terminal velocity is when your drag or your air resistance is equal to the weight. So when my weight is equal to the total air resistance, the force down is equal to the force up, then I'm not going to accelerate any more down, and I've reached what I'm going to call terminal velocity or terminal speed. Just as a fun side note, my son had this great shirt that's so dorky. Poor kid has a physics teacher for a dad, but he has a shirt that says terminal velociraptor on it, and the velociraptor is falling, and it says force drag up and force mass, force of gravity down, and they're equal to each other. Terminal velociraptor. Oh, you get it? Because it's like terminal velocity, but it's a velociraptor and he's a dinosaur. Oh, great toddler shirt. He outgrew it, unfortunately. Okay. And then air resistance could slow an object down. So if you have enough drag, enough air resistance, then instead of having both objects falling perfectly together at the same time, that one of the objects might get slowed down. In this case, the larger ball is being slowed down by air resistance, so it's falling a little bit behind instead of accelerating evenly. Okay, so that concludes our page walk. I'm going to finally just show you the problems that we're going to be working on. So here we go. Nice. All right, so last little note, the one thing that I think we might not have had was that pressure is equal to the force over the area. That is pressure equals force over area. Cool, just in case. So questions to hit. Chapter 4, we're going to go through 15 through 18, 20, 23, 24, 26, 27, 33, and 37. Chapter 5, 8, 9, 11, 15, 16, 20, 24, 29, 30, and 34. Show your work, show your needs and givens for the problems where it's relevant, or answer in a full sentence if it's not a needs and givens kind of problem. So if it's not a numbers word problem and you don't need to show needs and givens, that's fine. Just show your thinking and your work. All right, enjoy. and I will look forward to going over with those once you have finished them. All right, have fun, my friends.